We'll start with actual syllabus, the gradient of scalar field. Normally this can be asked for. What is gradient of a scalar field, or explain gradient of a scalar field giving its physical meaning. 5 marks. Let's go for a gradient of a scalar field. We'll consider here phi of x comma y comma z be a continuous scalar function which is differentiable scalar function, and the gradient of a scalar field function phi is defined as a vector. Gradient of a scalar field, say function phi of x, y, z is a vector. I'll write gradient of a scalar field is a vector. That means a scalar field we are converting into a vector field. Let us take this a scalar function which is continuous scalar function, and this function is differentiable. Let us write this. So gradient of a scalar field is a vector which is defined as grade phi. It is denoted by grad phi, G-R-A-D. Grad phi is equal to I, a unit vector, dou phi by dou x, plus j, a unit vector, dou phi by dou y, plus a unit vector k, dou phi by dou z, where I, j, and k are unit vectors. We have defined this gradient of a scalar field is defined as a vector, and it is given mathematically as this. When I say this is a scalar function, a scalar differentiable function phi of x, y, z, which has only magnitude, mathematically we have written this as grade of phi is equal to by this. That means a scalar is converted into vector or represented as a vector. When we say a vector, it should have components. So here the x component of this scalar function x, y, z is I dou phi by dou x. This is a vector represented by this, and its x component I dou phi by dou x is its x component. Hope you got this. Y component, that is j, unit vector j, dou phi by dou y. Say y component, and say k dou phi by dou z. Say z component. That means gradient of a scalar is a vector, and it is defined mathematically by this. This is x component, this is y component, and the z component. So after resolving this, in which I, j, k are unit vectors. Once we write this, I said this, let phi of x, y, z be a scalar differentiable function. The differentiable, the d phi, that is its differential, I'll write differential of this function dou phi by dou x dx plus dou phi by dou y dy plus dou phi by dou z dz. This function is a scalar function which we have defined it as a vector, and this is its difference differentiation. Its differential you can write. Hence we can say gradient of a scalar is a vector. Let me rewrite this. Okay. Let me consider, say here, if R is a position vector, we write this position vector is equal to unit vector Rx plus Jy plus K Z. Is the radius vector from the origin, as we have seen in a space. It's a radius vector from the origin. Its differential dr, let me write, this is equal to I dx plus j unit vector dy plus unit vector k dz. Its differential. Let me write the differential of this scalar function d phi. Scalar function is phi. Okay, its differential, say I dx unit vector plus j dy plus k dz into this. I'll write this as I dou phi by dou x unit vector j dou phi by dou y plus unit vector k dou phi by dou z. I treat this as d phi is equal to, I'll rub this below portion, d phi is equal to, say this is dr phi, dr position vector, and this is how we have defined a grade phi, that is gradient. Here the gradient phi, we are using many times this notation delta. This notation delta we write, that is, it is a differential operator and not the vector. Please keep in mind, this is a differential operator and not the vector. So I will write this as I, say, dou by dou x plus j unit vector here, dou by dou y plus k dou by dou z. It is an operator, del operator. It is called as del, del, read as del or nabla. And it is mentioned in the literature. This is nothing but operator, differential operator. So let me use that also. So this, we have written this. So we have come across this d phi is equal to dr grad phi, or say d phi is equal to grad phi dr, because it is a dot product. Now I can write this as del phi. If this can be written as del phi. So here d phi is equal to del phi, say here dot dr, or I can write this as del dot dr, this function phi. We want this. By definition, we have written this gradient of a scalar is a vector, and we have written it as in a mathematical form. Fine. We have defined mathematically, that is gradient of a scalar is a vector. Now, what is the physical meaning of it? That is important. The physical meaning of say gradient of a scalar function. I'll write physical meaning of gradient of a scalar function. Say physical meaning of, you can write significance in bracket. They asked this in the examination. Significance, physical meaning or significance of gradient of a scalar. Gradient of a scalar function. Fine. Okay. For this, we know the scalar field, that is temperature, say electric potential, and these scalar fields are represented by level surfaces. So let us consider two level surfaces. Here this is S1 is a one level surface, and close to that I will take S2, the another level surface, represented by a function phi and phi plus d phi. Fine. S1 is one surface, level surface. S2 is another level surface, represented by a scalar function phi and its incremental function phi plus d phi. It is in this scalar field. Let me draw this as a point here O. I will consider point A here, and say point B. This is point B, this is point A on this two level surfaces. Okay, so here this is R and this is position vector R plus dr. I will join these 2 points on any 2 points on this surface, that is AB, and I will call it as dr. From here, from point A, I will draw a normal, that is unit represented by unit vector, and it's this point, let me call it as C. The angle between this is theta. So here this is, say, dn, this, and it is n here. This is vector dr, this is r plus dr, this is origin. So let me explain once again. Consider two level surfaces S1 and S2. Phi and phi plus d phi are the scalar functions. We are considering any 2 points A and B on the 2 surfaces. R is the position vector from O of point A. R plus dr is the position vector of point B on the other surface S2. So we want to draw a line here that is joins A and B, and it is represented by dr. I am drawing a normal at point A, represented by unit vector n, that is AC here. Let me write mathematically OA as R, OB is, say, from the origin R plus dr, this is vector, and AB here is dr. Now, the least distance between 2 surfaces here is AC. The least distance between the 2 surfaces is AC, and that is along the normal at A. A is the point on surface S1. I have drawn here AC, the least distance between the 2 surfaces S1 and S2. called as AC, and this least distance is along the normal drawn at point A. Let me write this AC is equal to dn, the unit vector. Therefore, I can write this as dn is equal to, say, n dot dr, or we can write this is dr cos of theta. That is, theta is the angle between dr and n. Now, rate of increase of this function phi is a scalar function. Rate of increase of a function phi at A is maximum and the dou phi by dou r. It's the rate of increase of a function phi at A is given by this change of function with position. This rate of increase will be maximum provided, say, dou r is minimum. Hope you got this. If this denominator parameter dou r change in the displacement or a distance here or a position, if it is minimum, this will be maximum, and we are calling this dou phi by dou r is the rate of increase of a scalar function, and the rate of increase of a scalar function will be maximum at A where dr is minimum, and dr will be minimum when the least distance between the two surfaces, that is, dr is minimum at A, that is AC, the minimum distance, least distance along AC, that is along the normal, and so the rate of increase of a scalar function is represented by this dou phi by dou n in the direction of, say, unit vector n. Hope you got this. Dou phi by dou n. Let me repeat this. See, rate of increase of a function that is at A is given by this dou phi by dou r. Now, the rate of increase of the function at A is dou phi by dou r, and the rate will be maximum provided dr is minimum. This dr is minimum, that is along AC, because it happens to be the least distance between the two surfaces, that is along the normal at point A, that is along the unit vector. And this rate of increase of the function d phi by d, say dou phi by dou n in the direction of n is maximum. Rate of increase of a function is given by this along the direction of unit vector. So I will write here, that is d phi, differential of a scalar function phi, is equal to dou phi by dou n unit vector n. You can write this as dn, unit vector dn. Now, we got this. Fine. I will write this dn is equal to d phi is equal to, say, dou phi by dou n. Dn we have written somewhere, that is this n dr, unit vector n vector dr. By definition, I have written this d phi is equal to, say, del phi dot dr. We have written this. d phi is also del phi dot dr. It's by definition. Let us equate these two. So I'll write it here. So del phi dot dr, that is this, is equal to, I'll write this, that is dou phi by dou n, say n dr, or del phi is equal to dou phi upon dou n, say unit vector n, that is equal to del phi is equal to dou phi by dou n, that is grade phi, gradient of phi. Now, and this is a vector, grade phi is a vector, grade phi is vector. What is the meaning of this? So we say physical meaning or significance of a gradient of a scalar function is a vector. Gradient of a scalar function is a vector whose magnitude is equal to the maximum rate of change of a scalar function, maximum rate of change of a scalar function, and its direction is perpendicular to the level surface, and its direction normal to the level surface or perpendicular to the level surface. Hence, grade phi is defined as the gradient of a scalar function is a vector whose magnitude is equal to maximum rate of change of a scalar function phi, and the direction is normal to the level surface. This is its definition. Well, hope you got this. What we have done, let me revise. Hope you got this, because this is, say, two level surfaces. We have taken some point as origin. R is the vector, A and B, any 2 points, R and R plus dr are the position vectors. From the geometry we got the AB, the distance between two, and AC is the least distance, and we have written here this vector. So d phi, we got the maximum rate of increase of the scalar function, which is along the least distance. From the earlier definition we got this, and this is how the gradient of a scalar function whose magnitude is the maximum rate of increase of a scalar function, and the direction is normal to the level surface. This is about gradient of a scalar. That means in a scalar field, if a quantity is a scalar, we can convert that by finding its gradient as a vector. So this is a tool, mathematical tool. Suppose we have been given a scalar field. I want to find its that is equivalent, say, vector field. Let us take an example of this. What is the example for this? We have come across, this is a common example we have come across. What is the common example we have? Example, say let V be the potential. V is the potential, and this potential, electric potential, due to static charge. Due to static charge around a charged body. Fine. Then the electric field intensity at a given point. V is the potential, which is a scalar quantity represented by a scalar function. Electric intensity is a vector quantity. Now, here in this example, V is the electric potential. It's given a scalar function. Its electric intensity at any point is the greatest rate of decrease of this potential. Greatest rate of decrease of the potential V, that is E is equal to minus gradient of V. Gradient of V, and its direction is, say, normal to the electrical potential surface drawn in the electric field. So, negative gradient of a potential is electric field intensity. Hope you remember this. E is equal to, you have written minus dV by dx, and this is the relation between electric potential and the electric field intensity. We have done it many times in PUC. For 2 marks we have obtained this relation. This is a good example. Another example, if V is the potential energy by virtue of position, then we write this force is equal to negative gradient of potential del V. Many times we use this in physics. I have written here E is equal to minus gradient of V. Here it is electric potential. Here this is the potential energy. Potential energy. I can write this potential energy as a force. Now we can say from a scalar quantity like energy, potential energy, as the energy, the greatest rate of decrease of potential energy gives us the magnitude of force here. Magnitude of force, and the direction is perpendicular to the normal drawn at the surface, level surface. Here is V is the potential. We can write this as force is equal to minus grad of V, where V is, say, potential energy. This is electrical potential. This is potential energy by virtue of the position. So, gradient of a temperature is another example. Gradient of a temperature, grad of temperature, say T, is flow of heat. Is a flow of heat is an example. Flow of heat. Transfer of heat or flow of heat is an example of gradient of a scalar field. Gradient of a temperature is proportional to the flow of heat. Say proportional to the flow of heat. and this flow of heat is represented as a vector. So point here, to conclude, gradient of a scalar function is a vector. We have drawn the physical meaning of it. We have represented it mathematically. Please go through this. Please go through my notes as well as go through this video. If you are unable to understand, do contact me at this number. We'll continue it in the next video.